Hi, I'm Randall Heyman, a university academic. You're on one of my Corona Help playlists where I make quick turnaround videos to help educators and students during the coronavirus outbreak. If you'd like me to make a video for you, no problems. Just email me, coronahelpmathematics@gmail.com, or if you like, comment below any of my videos. So this is the second part of a video of two videos about solving this problem. Someone asked about this problem, and I gave a hint in the last video, and the hint was that you could use Euler's theorem or Fermat's little theorem. So I thought I'd show you that. There's another way to do it. I'll explain at the end if we get time. Okay, so let's just do a by the way, recall the factor theorem. If fx is a polynomial and if a equals 0, then x minus a divides fx. I'm going to be a bit tight on time here, so I might just leave that with you. Look it up if you want. Try it out with a few polynomials. You'll pretty quickly see how it works. But if you've got any questions on that, by all means, just give me a buzz. Contact me and I'll see what I can do. Okay, now let's talk about Euler's theorem, or you can either use Euler or Fermat. Euler is a generalization of Fermat, so I'm just going to use Fermat's little theorem. Fermat's little theorem. If P is prime and A is an element of ZP, then A to the P minus 1 is congruent to 1 mod P. I've got a video on that Fermat's little theorem made easy if you want to have a look at that, and that'll help you out. I'm just trying to think about 0 here. I don't think 0 can will work with 0. Not that we're worried about 0. That doesn't work for 0, does it? No, so let's just go take out 0. Yep, okay. Okay, so now let's look at solving this. So let fx equal x to the p plus alpha. Okay. Then fa equals a to the p plus a. Let's make it f minus a, I think would be better. Let's make it minus a. F minus a equals negative a to the p plus a. Well, that's equal to negative 1 to the p a. Oh, I don't need the bracket there, do I? A to the p. A to the p plus a. Now, it equals, I'm going to just do the case where the prime is odd, which is all the primes apart from 2. I'll worry about 2 later. So I'm just going to say this bit here, negative 1 to an odd power is negative a to the p plus a. So I'll put here if p is odd. Then what we can say is then negative a to the p plus a is, well, this is actually negative a to the p minus 1 times a plus a. And this is now equivalent or equal, doesn't really matter, negative. So negative, this a to the p minus 1 here, if we look up here, is equivalent to 1. So I'll put negative 1 times a plus a, and is equivalent to, well, negative a plus a is 0. And I'll put in here by Fermat. Okay. So what have we done here? We've shown, so f of minus a, which is what we started off with here, is equivalent to 0 modulo p. And so then, thus, by the factor theorem, if x plus a divides fx, which of course is equal to what we're interested in. And then I suppose we could say if p equals 2, so now it's not odd, then we have fx is equal to x squared plus a, and you can just go through the cases, I suppose. Well, the only one is 1, so a, the only value of a possible, modulo p, this is mod p, is a equals 1, and then observe that x, so this is going to be x squared plus 1, so x plus 1 times x plus 1 is equivalent to, well, you get x squared plus 2x, but the 2x just disappears because we're modulo 2, so the 2 disappears, so plus 2x plus 1. So x plus 1 divides x squared plus a for all a modulo mod 2. Oh, I should write it in properly, modulo 2. So I think that'll work. Now there's another approach, or I think you can just do this, x to the p plus a. What we're saying is that, what we've shown is that x plus a is always a divisor. So you go x plus a, and then you say, well, what am I going to have to put in this part to make this work? Well, I've got, let's just see, we've got an x here, and we need xp to the p, so I better make this term x to the p minus 1. Now once I do that, if I look here, I'm going to have to multiply this by this, which will give me ax to the power of p minus 1, which I don't want because I don't have it over here. So I'm going to have to get rid of that, and the way I get rid of that, I think, is if I go minus a x to the p minus 2, because when I multiply that by that, I'll get minus axp to the x minus 1, which is what I want to get rid of. But now the problem is I've got this one by this one, so I've got to get rid of that, and the way I do that is I go plus, I think it is, plus a squared x to the p minus 3 plus, or then the next term will be minus dot, 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 dot. And then right at the end, the last term, I've got this a here, and I need to have a at the end. So I must have 1 at the end, plus 1. So if I go to red, put plus 1, plus 1. Now the only thing I need to think of now is, do I need to have an a term here? So this one here, let's have a think about this one. This one is a to the 1, x to the p minus 2. So this powers add up to p minus 1. So maybe I need to put here, this will be a to the p minus 1. And a to the p minus 1 is 1. So yeah, so that'll be fine. You could write here, if you wanted, you could write a to the p minus 1. Yeah, in fact, maybe you should do that just to plus times, if you like, x to the 0. That's a better way to put it. Then what happens is there's all a very logical pattern of how I've constructed that second factor. And then by Fermat. Well, actually, it doesn't really matter. At this stage, we've proven that it's reducible. So x to the p plus a is reducible. And we're done. If you've got any questions on that, or any aspect of mathematics, drop me an email or comment below any of my videos.